All right, for this topic, we're going to talk about the type of zeros of polynomial functions. If you have been following this lesson series, you're going to see how all these pieces connect together. So we're going to talk about the types of zeros, the rational root theorem, sometimes called the rational zero theorem, just depending on your instructor, finding all the zeros that go for a polynomial function, properties of those zeros, the fundamental theorem of algebra, Descartes Rules of Signs, that's how I said it, Descartes, because it sounds cooler, Linear Factorization Theorem, and of course, common mistakes and key takeaways. Now, my goal of this lesson is not for you to memorize the theorems and all of that, but just to memorize the logic and what tools that you can use in order to do well on this assignment, okay? So let's get started. So there are three types of zeros. Really, I want to say two. You'll have real zeros and imaginary zeros, but what you're going to see when you're looking for the zeros of this polynomial functions, you're going to see rational zeros, which are your integers and your fractions. You will see irrational zeros, which are your radicals, like square root of 2, square root of 4, your decimals that repeat on and on that don't have an ending. Those are your irrational zeros. And then now we introduce or bring in imaginary zeros. So let me show you what I drew here. So this is my numbers cloud. So all of the numbers in the world start at the top here with these complex numbers, okay? All numbers come from the complex numbers. And you see how I have this a plus bi? Well, the a represents your real. That's the real part. So the numbers that you see in math, see all the time, that you use all the time. And then this bi, that little I, that represents the imaginary part. Okay, and the b is just a number, and then the real part is a number. But when you see the I attached to it, that's your imaginary part. So again, all the numbers in the world come from complex numbers, but you're normally used to seeing these. Okay, so these are your real numbers. So you have real numbers, you have imaginary numbers, and under real numbers is where you see your rational, your irrationals. Your rationals are the ones that you normally use all the time: integers, fractions, counting numbers, all of that. Irrationals, that's where you have like your radicals, and then your repeating decimals. Like I'm just gonna make up one. But the ones that go on and they don't stop, that's what falls over there. So when we're going through these polynomial functions, you're going to see two types: real numbers and imaginary numbers. But under the real numbers, you can have rational zeros or you can have irrational zeros. So again, if you have a polynomial function, there's a way that you can find the zeros. Can you graph them? Yes, absolutely. But let's say that you don't have a graphing calculator. Let's say you're having trouble factoring what you're looking at. There are ways for you to find the zeros using, and this first way we're going to talk about is called the rational root theorem. I was going to say using the rational root theorem, but I haven't told you what it is yet. So what the rational root theorem basically says is that if you have a polynomial, then P over Q is a rational zero. Rational meaning you have your rational numbers and your irrational numbers. So rational means that it's an integer or a fraction is basically what it's saying. P over Q is a rational zero. Remember, if it's a zero of the polynomial function, that means it is a root, it is a solution. Then you can write the numbers for P are going to be the factors of the constant. And then the numbers for Q are going to be the factors of the leading coefficient. Remember, the leading coefficient is the number that's tied to the leading term, which is the term with the highest power. And then your constant is going to be at the end. It's not tied to any specific variable. So essentially what this rule says, or this theorem says, is that this theorem will help you find a list of all the possible rational zeros, not irrational, not imaginary, but rational zeros for a particular polynomial function. And once you have the list of zeros, then you can kind of start going through them to see which one or which ones are an actual factor of the polynomial. Because if you can factor the polynomial, you can break it down, you can graph it, you can find out what the zeros are. So let's see how this works. Next page. So to list all the possible rational zeros, not irrational zeros, not imaginary zeros, but rational zeros, what you do is they just use this to represent what you're doing, but the top is the factors of the constant term, which we know this is the constant term, and then the Q is the factors of the leading coefficient, which is the leading coefficient that's tied to the leading term, okay? And this is division. This is division. So you're dividing those numbers on the top by every number on bottom. So every number on top will be divided by every number on the bottom. So like, let's look at this one, for example. We have x cubed plus 2x squared minus 5x minus 6. List the possible rational zeros, meaning what are the possible rational zeros for this? Now, can you try to factor this? Yeah, but you can't do factor by grouping because things just aren't going to work out the way you want them to work out. But you can factor this. And how do you factor this? Well, let's see what the possible zeros are, the possible rational zeros are, and that'll help us get to our answer quicker. This is the constant, right? So I'm going to put -6 here because that's our constant term. And then what is the leading coefficient? The leading coefficient is 1. Okay, because this is the leading term. The number tied to the leading coefficient is 1. So I'm going to put that there. All the factors of 6. Remember, the factors are the numbers that you can multiply together to get the value that you're looking for. So all the numbers that will give me -6, if you think about it, and I'm going to write it out one by one. You have 1 times 6, right? You have -1. I'm saying 1 times 6. 1 times -6 if I wrote it that way. But let me list them out first, and then I'm going to show you what I'm talking about. So 2, -2. We have 3, -3, and 6, -6. And you're probably like, well, Dr. B, why is it all of those? It is all of these because you can have positive and negative that will give you negative. For example, 1 times -6 gives me -6. -2 times +3 gives me -6. -1 times 6, -6. Or 1 times -6 gives me -6. Or -3 times +2 gives me, see what I'm saying? So it's really all of them. And normally what you do to kind of get your list together, if I were to draw a line in here, another way of writing it, kind of like a shorthand way, just do plus or minus. So it's plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are all the factors of 6. Now, what are the factors of 1? 1. I was going to write plus or minus 1, but it's really 1 because 1 times 1 gives me 1. Or you could say -1. So we'll say negative because -1 times -1 is 1. That's how we'll do it, okay? So now what it says is, if we go back one, you take the factors of the constant and divide them by the factors of the leading coefficient. These are all our factors of our constant, which was -6, and we're going to divide them all by the factors of the leading coefficient. Well, it's going to be all of these divided by 1, right? Yep. So let me write that out. So if I were to write it out exactly how it looked, you had your P, right, over Q, which is the factors of the constant, which is going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, right? And that's all going to be divided by plus or minus 1. Well, we know if you take this divided by that, that's going to be 1, right? 2 divided by that, that's going to be 1. 3 divided by that, that's going to be 3. Sorry. 2 divided by that is going to be 2. 3 divided by that is going to be 3. And 6 divided by 1 is going to be 6. So the list of all the possible rational zeros, not imaginary, not irrational, but rational zeros, is plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So that is what the rational root theorem, the rational zero theorem does. It gives you a list of possible zeros to start with so that you can start breaking down whatever polynomial function that you have. So it kind of gives you like a head start. And you want that head start. You want to make sure you know where to start, because a lot of students like, where do I start? Well, start with the rational root theorem so you can see, well, what possible numbers can I have as root? And to prove that it has these, I'm going to show you this graph. Now look at this graph here. So we know that these are the possible rational zeros, but as you notice, there's only 3. And we know that zeros represent x-intercepts, right? The zeros are the same things as x-intercepts. And we know that x-intercepts is where you set y equal to 0 and solve for x. So your zeros and x-intercepts are related. They're the same thing, and they essentially help you write as factors for the polynomial. So this point right here, this is the point 2, 0. This point right here, I'll put it right here. That's the point -1, 0. Forgot my sign. -1, 0. And then this looks like 3. -3, 0. So the 3, so out of this whole list, because that's 2, 4, 6, 8, there were 8 of them. So out of this whole list, the actual zeros, and I'm going to write that here, I'm going to say the actual zeros, and I know they are the actual zeros because we literally have the graphs, are x equals -3, x equals -1, and then x equals 2. So there's 3 of them. And I want you to notice something. See the degree on the polynomial is 3? That means I should have 3 zeros, which we do. So the actual zeros, -3, -1, and 2. What's the relationship between the zeros and the x-intercept? Again, when we look at the graph, all of the zeros cross the x-axis. All of the zeros are where y is equal to 0. So these are x-intercepts, okay? So here I'm going to put they are the same. I'll put they are. You're probably like, what? So they are the same. The zeros and the x-intercepts are the same. You just write them differently. So up here, we wrote the zeros as x equal. But if you were to write them as x-intercepts, this would be -3, 0. This would be -1, 0. And this would be 2, 0. Okay, they are all x-intercepts. And then it says, does the number of zeros match the degree? Yeah, we found 3. When we looked at the graph, there were 3 of them. And the degree of the polynomial, this one, is 3. So yes, I'm going to put yes here. So you see how it kind of makes it easier. That way you don't have to try to guess, can I graph this? Yada, yada, yada. You just use the rational root theorem and it will give you a list of possible zeros. Now, this particular example, it just says, okay, now I want you to find all the zeros. So not just the rational ones. If there's any irrational ones, I want you to find them. If there's any imaginary ones, I want you to find them. So they want us to find all the zeros. But what we're going to do, let's start first with the possible rational root theorems, because if I can get the rational ones, the ones that I can see on a graph, it'll make it easier for me to find the other ones. So remember, it's the P over Q, right? And the P represents the constant term. So we take the constant term and find its factors, and we divide it by the leading coefficient and its factors. So let me write it this way. We have -3, right? Matter of fact, I'm going to put -3, and then I'm going to put, no, I can put it here, -3, and I'll put 4. So what are the factors of -3? Well, the factors of -3 are ±1 and ±3, right? What are the factors of 4? ±1, ±2, and ±4. Well, you're like, Dr. B, how did you come up with that? Because 2 times 2 is 4. 1 times 4 is 4. And then 4, is that -3? Yeah, -3. And then either 1 times -3 or -3 times 1, that would give you 3. So these are all the factors. Now, remember the rational root theorem told us that when you write your list out, you take every number up here and you divide it by every number down here. So I'm going to do that. I'm going to take 1 and divide that, and I'm going to take the 3 and I'm going to divide it by everybody, okay? So if I write that, I have ±1 divided by ±1, right? ±1 divided by ±2. I have plus or minus, what is that? 1 divided by ±4. So far, so good. Top on every number on bottom. Now let's do the 3. Let's take 3 over those, okay? So then I have, ±3 divided by ±1. I have ±3 divided by ±2. And then I have ±3 divided by ±4. You see that? Good. So now when you do the division, we know, like for example here, 1 divided by 1 is 1, right? this is 1/2, this is 1/4, this is 3, this is 3/2, this is 3/4. So let's write them simplified. Okay, so this is going to be plus or minus 1. I can write it in a different color so they stand out. So we have plus or minus 1. We have plus or minus 1/2, plus or minus 1/4, plus or minus 3, plus or minus 3/2, and then plus or minus 3/4. Okay, so this is the list of my possible zeros, my possible factors for this polynomial function up here. Now, how many do we have? That's 2, 4, 6, 8, 10, 12. There's 12 of them. There's 12 of them. So how do we know which one is there? This has a 5, so we should have 5 of them, but it doesn't mean that all of them are rational. Some could be irrational and some could be imaginary. You see what I'm saying? Now, we're going back. If we find that one of these values here is a 0, then that means we can write it like this and it becomes a factor of our f of x. Let me say it again. If we find that one of these zeros is a factor, meaning if I plug it into my f of x and I end up with 0, that means that whatever zero that was that I plugged into f of x, if I get 0 on the end, that means I can write it as x minus whatever this c is, and it's a factor of f of x. So how do we test that? Good old synthetic division. Okay, so here's my list. Now you notice with my list I put them in order. So 1, 3, and then I just put all the fractions together in order. So let's start testing. You're like, you test all of them? I hope not, because if you go through and you have to test all 12 of them, it's going to be But what I'm going to do, just for the sake of this lesson, I'm going to go through them so you can see, not all 12. I'm not going through all 12. I'm going to go through some of them so that you can see the process of how it works. But once you get really, really good at factoring and finding zeros, you'll know which numbers to pick automatically. You won't even waste your time. So with synthetic division, remember we have our little hut, right? And then you'd have your line. And then right here, we put all of our coefficients that are on our function. Remember, you have to fill in any that are missing. So we have x to the 5th, we have x to the 4th, but if you notice, we don't have an x third or an x squared. So we're going to have to plug those in with zeros. And then your c value goes here. And if we get a remainder of 0, then we know that this c is a 0, and therefore we can write it like this, and it becomes a factor. And you'll see how it works, okay? So let me put my c here. So I'm going to put 1 here, and then I'm going to write my coefficients. So I have 4, I have 12. I do not have an x cubed. I do not have an x squared. I have -1 and then -3. You see that I'm keeping the sign. Let me extend my line here. And our goal, hopefully, is to get a 0. Let's see if we get a 0. And remember, with this, everything is added. Okay? So the first number comes down. I have 4. Bring my first number down. 4. And then I'm going to say, okay, 4 times 1 is 4, right? And then we add. 12 plus 4 is going to give me 16, right? And then you're going to say, okay, 16 times 1 is 16. 16 plus 0 is 16. So far, so good? And we just continue. 16 times 1 is 16. 16 plus 0 is 16. And then you have 16 times 1 again is 16. And then 16 plus, what is that, -1 is going to give us 15, so it drops. And then 15 times 1 is going to give us 15. And then 15 plus -3 is going to give us 12. Okay, so this remainder here is not 0. And because the remainder, remember, synthetic division is just like doing long division. If you get a remainder of 0, then we mean that we know that that number is a factor. Remember, if you were to take 4 and you divide it by 2, you would say, oh, okay, 2 times 2 is 4, right? And when you subtract, you'd have a remainder of 0. We know 2 is a factor of 4. This is the exact same concept, just with polynomials. So if I do this division with this root, and if I end up with the remainder of 0, then we know that this root is this 0 is a factor, but this one is not a factor. So remainder is not 0. C equals 1 is not a factor. Okay? It is not a factor. So 1 doesn't work. So what do? Try another one. Okay? Now remember, we're going to go through this till we find one that works. So let's try another one. I hope I didn't switch too fast. The remainder was not 0. So C equals 1 is not a factor. So let's set it up again. We have our, what do you call it? Our line. Let me fill this in. So we have 4, 12, 0, 0, negative 1, negative 3. And our goal is to end up with a remainder of 0. And then let's get our C value of negative 1. Okay, negative 1. Remember, first number comes down. So far, so good. So we have 4. And we're going to take 4 times negative 1 is going to be what? Negative 4. And then, everything's added, okay? So 4 times negative 1, negative 4. Negative 12 plus negative 4 is going to give us 8, right? So far, so good. And then 8 times negative 1 is going to be negative 8. Okay, 0 plus negative 8 is going to be negative 8. So negative 8 times 1 is going to be a positive 8. And then 0 plus 8 is obviously 8. And then 8 times negative 1 is going to be a negative 8, right? A negative 1 plus negative 8 is going to give me a negative 9. And then negative 9 times negative 1 is going to give me a positive 9. And then negative 3 plus 9 gives me 6. Same drama. Didn't work, right? Okay, so again, the remainder is not 0. Okay, so C equals negative 1 is not a factor. Okay, it is not a factor. So far, so good. Okay, let's try this one. Let's draw our little hut. Okay, draw our line. We got 4, 12, 0, 0, negative 1, negative 3. Again, my desire for you is not to have to go through this every single time. But when you get really, really good at seeing the numbers, they'll stand out to you, I promise. Okay, let's keep going. 4 times 3, that's going to be 12, correct? 12 plus 12, that's 24. 24 times 3, get your calculator. 72, okay. 72, 0 plus 72 is 72. And then 72 times 3, that's going to give us 216. Ooh, I got to write skinny. So then 0 plus 216 is 216. And then y'all already know this ain't going to work, right? If you see it's not going to work, you can stop. But because this is a lesson, I'll keep going. So 216 times 3, 648. Yeah, this not going to work. Let me see, 648. And then 648 plus negative 1, which we know that's going to be 647. Okay, let me squeeze that in there. And then 647 times 3 is 1,941. Now, if I were doing this, let me see. I would have stopped already because it's clearly not going to work. Okay. Remainder is not 0. C equals 3, not a factor. Okay. One more time. Okay, don't give up on me. One more time, one more time, one more time. Okay, one more time. Let's come on, one more time. I think that's the part people hate about finding zeros because it can take that long, but I promise you, you get really, really good at finding factors. You won't have to go through this all the time. It won't be this much drama all the time. So 0, 0, -1, -3, and then draw that, and then our C goes here. First number comes down. You have 4. Okay, let's keep going. 4 times -3. Good. -12. That's not the right color. That's not the right color. Lord. Sorry. -12, right? Oh, and these are added. So 12 plus -12, we know that that's 0. So far, so good. 0 times -3 is 0. 0 times -3 is 0. Don't y'all judge me. 0 plus 0 is 0, right? Fixed it. 0 times -3. 0 times -3. 0. 0 plus 0. 0. 0 times -3. 0. Y'all see what's happening? I think it's going to work, right? -1 plus 0. -1. And then -1 times -3 is going to give us a +3. And look at that. Look at that. We get a remainder of 0. That's what we wanted. That's what we wanted. So our remainder is 0. So C equals -3 is a factor. And because C equals -3 is a factor, we can write it as x minus the C. Remember, it said write it as x minus C on the factor theorem. Okay, so that means that this is a factor, or it's one of the factors of this polynomial. So if we were to factor this polynomial, when you factor it, you write it like that. It's saying that this is going to be one of them. Is essentially what they're saying, and we're happy. We're happy for that. So because C equals -3 is a 0, it's a factor of, or C -3 is a 0, then that means that x minus is a factor. Okay, but if I were to rewrite this, you don't want x minus a negative. Remember, a minus and a negative, you can write it as x plus 3. So that's what it'll look like. Now, what you want to do is a factor. Make sure you put it in the format of x minus c first before you convert it, just to avoid any issues. So since x minus 3 is a factor, that means when we factor this and we write it like that, one of these is going to be in here, or that's going to be in here. Now, you're like, well, what's the other one? Well, when you do synthetic division, what happens? Remember, you start with an x to the 5th, but when you write this part, it becomes an x to the 4th. So this part right here, this is really 4x to the 4th plus 0x cubed plus 0x squared plus 0x minus 1. Okay, that's what this translates to. So you go a degree down. So this is really 4x to the 4th. Let me put an equal sign. 4x to the 4th minus 1. Because we started with x to the 5th, but when you do division, it always goes lower. So 4x to the 4th minus 1. So that means we can take this, which I think I'm going to write it. Yeah, we can take 4x to the 5th plus 12x to the 4th minus x minus 3. And when we factor it, it can be factored into x plus 3 times 4x to the 4th minus 1. Y'all see that? Now, if we want to continue factoring this polynomial, does this look like anything to you? What about a difference of squares? Do you see it? The difference of squares? Yeah, that's 2x squared minus 1 squared. This is 2x squared minus 1 squared. Okay, it's a difference of squares. A difference of squares. So a difference of squares means I can take 2x squared plus 1, 2x squared minus 1. Okay, so let me write that. So this becomes x plus 3. And then this piece factors to 2x squared plus 1 times 2x squared minus 1. Okay, now, am I done factoring? Am I done factoring? Yes, because that's as far as it can go. That's as far as it can go. And this is as far as it can go. Now, this tells us we have 5 zeros. But you're looking at this, you're like, well, this is a factor, right? This is a factor, and this is a factor. We need 2 more. Well, where are the 2 more? Well, I'm pretty sure they're hidden in here. So what you do now, when forgot the name of the theorem, but if you find a factor, you can set it equal to 0 to solve for x, because remember, your zeros are the same thing as x-intercepts. So let's figure out where all of the x-intercepts are to get all of the zeros, okay? Let me see if I have room. Let me write here. So then we're going to take x plus 3 and set it equal to 0. And we're going to take 2x squared plus 1 and set it equal to 0. And then I'm going to write this one in another color. 2x squared minus 1 and set it equal to 0. Okay, that's what we're doing. All right. All right, so now let's do the math. Okay, let's do the math. We can put it right here. Let's do the math. So let's solve each of these for x. Okay, so I'm going to subtract 3. I'm left with x equals negative 3. So we know that's 1. So we need 4 more. This, I'm going to subtract 1. I'm going to subtract 1. Okay, and then I have 2x squared is equal to negative 1. I'm going to divide both sides by 2. And then I have x squared, because these divide each other, okay? Excuse me, is equal to negative 1 over 2. And then I'm going to take the square root of both sides. I'm taking the square root because this is squared, okay? So then I'm left with x is equal to plus or minus the square root of negative 1 over 2. I write big, but that's okay. We're going to keep going. I'm going to stop there for a second, and I'm going to do this one the same way. If you notice, it's going to be very similar. So plus 1, right? So then you have 2x squared is equal to 1. We're going to divide both sides by 2. These divide each other evenly. So I have x squared is equal to 1/2. And then I'm going to take the square root on both sides because I have a squared on the x. And then I'm end up with x equals plus or minus the square root of 1/2. Now, these aren't simplified all the way. This is, but these two aren't simplified all the way. So we need to keep going. Okay, so this one, this is plus or minus the square root of negative 1 over the square root of 2. And this let me write this right here. I is equal to the square root of negative 1. So that's going to be imaginary, okay? I is equal to the square root of negative 1. So this is equal to x equals to plus or minus, before I do that, no, I can do that. I over the square root of 2. Now, you normally don't leave radicals in the denominator. You have to rationalize the denominator. So I need to multiply top and bottom by the square root of 2. The square root of 2 times the square root of 2, that's equal to the square root of 4. But we know that the square root of 4 is equal to 2. So the denominator becomes 2, and then the numerator just becomes I times the square root of 2. Okay? So let me write that. That's going to be plus or minus I times the square root of 2 over 2. Okay? Plus or minus I times the square root of 2 over 2. Okay? Now let's do this one. So you notice that's 2 imaginary roots. So now we have 2, and 1. So we have 3. So we need 2 more, right? So let's finish with this one. This one's going to give us 2 also. So same thing here. You can't, this is the square root of 1 over the square root of 2. You don't leave a radical in the denominator. You have to pull it out. So that this is the square root of 2 times the square root of 2 is the square root of 4. But we know the square root of 4 is equal to 2. So the denominator becomes 2. Cool beans. So x equals plus or minus the square root of 2 over 2. So here's our other 2 factors. So now we have a total of 5 because we have 2 here, and 1 here. Cool beans? Yep. So this was a rational zero. Rational are your regular numbers. And then you see the irrationals. Irrationals contain your radicals or your repeating decimals. And then your imaginaries have the i's in front of them. And when we did plus or minus, that's what gave us 2. So we had 2, 4, 5. And it matches the number of zeros right there. Cool beans? Okay, cool beans. So just quick properties which you have seen what we worked through. If a polynomial has a degree of n, then the equation has n zeros. You might not know what type of zeros they are because they could be rational, they could be irrational, they could be imaginary, but the degree of the polynomial should tell you how many zeros that you're going to have. If you end up with an imaginary number as a 0, you bring in its partner. So if you have a plus bi is a 0, a minus bi is also going to be a 0. And I'll show you an example of that. Okay, so imaginary numbers, their zeros come in pairs. So the fundamental theorem of algebra says if f of x is a polynomial of degree n, where n is greater than or equal to 1, meaning you have an x value, because that's x, that would be x squared, x cubed, plus x squared plus x. So notice on all of these, they have a degree greater than or equal to 1. The first one has a degree of 1. The second one has a degree of 2. The third one has a degree of 3. Okay, so that's what that means. Then the equation f of x equal to 0, meaning you set y equal to 0. When we're talking about functions, we use f of x. Y and f of x are the same thing. Has at least one complex 0. And you're like, what does that mean? Complex 0 just means it has at least one complex 0. It's going to either have a real 0, it's going to have an imaginary 0, but it's going to have at least one is what it's saying, which that's what we found. If you think about it, it's like, duh, right? So you'll have a real 0 or you'll have an imaginary. And remember at the very beginning of this lecture, I showed you the complex numbers crowd. This is where it's in the form of a plus bi, but b is equal to 0. And these are in the form of a plus bi, but b is not equal to 0. The imaginary part exists, and on this side, the imaginary part does not exist because it's 0. Okay? So if a polynomial has a degree at least 1 or higher, then it has at least 1 0 is basically what they're saying. You just have to determine, is it irrational? Are all the zeros rational? Or are the zeros irrational? Are they imaginary? You have to find what zeros there are, but just know there is at least 1 0. You just have to find it. So let's do this one. We're gonna just go through the steps. We're gonna list all the possible rational zeros. We're gonna use synthetic division to test to see which one we have, and then we're gonna find all the remaining ones. Now, I promise you we're not gonna go through 12. We're not gonna go through 12 of them, okay? I won't do that to you. We're not gonna go through 12 of them. We're just gonna go through a couple, and just so you can see from start to finish how it works. All right, let's list all the possible zeros. Remember, it's the factors of 45 divided by the factors of 1. So our P are going to be the factors of 45, which is what, plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 9. Was that 15? I'm totally guessing. Let me see. 1, 3, yeah, 1, 3, 5, 9, 15, and 45. Y'all check my math. I believe all of those, looking at my notes, 1, 3, 5, 9. Good. We're good. And then our Q are all the factors of 1, which is plus or minus 1. We're going to take all of these and divide them by 1. So if all of them are divided by 1, what is your list? My list is plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 9, plus or minus 15, and plus or minus 45. That is what? 2, 4, 6, 8, 10, 12. We are not going to test all 12 of these. Okay, but because I'm looking at this polynomial function, I have an idea of which ones I want to test. I'm going to test 3 because we got 45, we got 9. So I'm like, okay, let's test 3. So I'm going to will it let me paste it? Okay. I'm going to put this right here. Is that okay? Those are our possible zeros, all right? Let me put it right here. Okay. So let's test. We're going to say C is equal to 3. Let's test 3. I'm guessing just because I see the 9 and the 45. So let's just try it. And that's what I'm saying. When you start looking at these numbers, you should have an idea of which ones you want to try. Now, it goes cubed, squared, x, so that's good. So I'm going to put these in order. I have 1, -5, -9, and 45. My C is 3. The first number comes down, right? So we have 1. 1 times 3 is 3. -5 plus 3, negative 2. -2 times 3 is 6. Trying to make sure my math is, okay, 6. Cool. Already see something I did. Oh, negative. Y'all see? -2 times 3, -6. I'm talking about watching my signs. I didn't even watch my signs. And then -9 and -6, that's going to be a -15. And -15 times 3. I know 3 works because when you do factor by grouping, that works. And so I knew I had messed up, but let's keep going. 15 times -3, that's going to be a negative 45. And boom, we get a remainder of 0. That's what we want. So because we have the remainder of 0, we know that this is a factor. Not is a factor, sorry, is a 0. And because that is a 0, x minus 3 is a factor. Okay, x minus 3 is a factor. Don't lose that. X minus 3 is a factor. And now we're going to go from x cubed to x squared, right? So this is going to be x squared minus 2x minus 15. You're like, Dr. B, where'd you get that from? We started with x cubed. We divided this polynomial by this 3. And when you divide, it goes down a level lower. So we have this x squared minus 2x minus 15, and then we have x minus 3 is a factor. Okay, so x minus 3 is a factor, and x squared minus 2x minus 15 was the quotient. So now to find all the remaining zeros, let's see if we can continue factoring. So because that is a factor, then x cubed minus 5x squared minus 9x plus 45, I can write it as x minus 3 times x squared minus 2x minus 15. We can factor this. So that's x minus 3. And then times, that's going to be what, x, 5 and 3. Yeah, x plus 3, x minus 5. Okay, check my FOIL. X plus 3 times x minus 5. So then, because these are all factors, that means I can take x minus 3, set it equal to 0. X plus 3, set it equal to 0. And then x minus 5, set it equal to 0. It says we're supposed to have 3 zeros, and we found 3. So I say we've done good. Okay, so I'm doing all of them at the same time. So we have x equals 3 is a 0. We have x equals -3. And we have x equals 5. Cool beans? Okay, cool beans. So we found the 3 We found the 3 zeros. Okay, so that's how it works from start to finish. Look at the numbers and kind of give yourself an idea of what to pick. Don't test all 12 unless you want to, but I wouldn't do that. Okay, another tool that really helps with there we go. Another tool that really helps with finding zeros, or at least giving you an idea of what zeros to pick, is Descartes, and that's how I say it because it sounds cool. Descartes Rule of Signs. So basically what you do is you count the sign changes between each term in your polynomial, and then it will give you an idea of how many real zeros, not imaginary, real. You have your real, you have your imaginary. Complex numbers, real, imaginary. This tells you how many real zeros. It doesn't tell you if it's rational or irrational. It just tells you if it's the real zeros. So we're not even thinking about imaginary at this point. If you're noticing what we've done, it's easy to find the rational, the reals first, and then come in with the imaginary. So that's why we're doing it this way. So the number of positive real zeros is the same as the number of sign changes in f of x, or less than the number of sign changes in f of x by a positive even integer. I'm going to show you what that means, and I'm going to show you how to do it every single time. Don't try to memorize this. The number of negative real zeros is the same as the number of sign changes in f of negative x when you plug in negative x for every x, or less than the number of sign changes in f of negative x by a positive even integer. Essentially what you do, count the number of sign changes for positive real zeros, count the number of sign changes in f of x, and then decrease it by 2. And those are all your options. Same thing with the negative real zeros. Let's do an example so you can see it. So like a polynomial function has 7 sign changes. So that means it's going to have 7 sign changes, or now decrease it by 2 until you get to the end. 5, 3, or 1. You're not going to have a negative number of sign changes. So this says you can either have 7 real zeros, 5 real zeros, 3 real zeros, or 1 real zeros. And if you notice, all of these are minus 2. That's where they said that minus even integer. That's what they mean by that. This one says a polynomial function has 4 sign changes. So that means it's going to have 4 positive real zeros, or decrease by 2. It can have 2, or it can have 0. So you can have 0 positive real zeros because all 4 of them could be imaginary. See what I'm saying? Let's look at this one. Find the positive real zeros. Look at the sign changes between each term. It starts off positive, it stays positive, it stays positive, it stays positive. So there are none. That means this particular polynomial function, it doesn't have any positive real zeros. So when you get your list of possible rational zeros to test, don't pick the positive ones. Why? Because it's telling you right here there aren't any positive ones. So that's what I'm saying. Don't memorize the theorems. What tools can you use to save yourself some time, okay? This says there aren't any positive ones. Why? Because there's literally no sign change in f of x. Let's look at the negative. So negative means substitute every x with the negative x. So f of negative x, and I'm just going to write it, cubed squared plus 7. We're going to substitute negative x. So negative x, negative x, negative x. I took negative x and I substituted it into every single x. This comes out to be negative x cubed, right? This is going to be 2x squared minus 3x plus 7, because this is multiplication. Okay, you're multiplying. This comes out to a positive x squared, and you're multiplying. So now count the number of sign changes. We go from negative to positive. Matter of fact, let me get we go from negative to positive, that's 1. Positive to negative, that's 2. Negative to positive, that's 3. So we had 3 sign changes, right? I'm going to put 3 sign changes. So that means we have 3, subtract 2, 1, negative, real zeros. So you can have 3, subtract 2, 1, negative real zeros. So we have no positive. We could have 3 or 1 negative. if we have one negative real zero, we still need three more, right? We still need three more. So the other two are probably imaginary. So that's what I'm saying. Use this to help you decide what to pick. So if you think there's three of them, if you find one, there might be another one. If not, you'll see when you do the factorization because you might come out with imaginary. So I think I got the graph of this one. So yeah, if you look at the graph of this one, there's only one. And that's what it told us. We're either going to have three or we're going to have one. So we had positive real zeros. There was none. And we had for the negative, it was 3 or 1. And as you can see here, based on the graph, we only have 1. So that means what's remaining are probably going to be 2 positive. And it has to be 2 positive imaginaries remaining, not positive, remaining 2 imaginaries. Not positive, but 2 imaginary zeros. Because remember the imaginary numbers come in pairs. So when you graph it, you find the 1, okay, which looks like, I'm assuming that's -1. I didn't draw it to scale, but I'm assuming that's -1, 0. So then the other two are probably going to be imaginary or are imaginary. Okay, look at this one. Let's count the sign changes. Okay, let's count the sign changes. We go from positive to negative, that's 1. Negative to positive, that's 1. Positive to negative, that's 1. Negative to positive, that's 1. And positive to positive. So we have 1, 2, 3, 4. We have 4 sign changes. And because we have 4 sign changes, we're going to have 4, subtract 2, 2, subtract 2, none, positive real zeros, okay? So if you get the first number of sign changes and then just keep subtracting 2 until you can't subtract 2 anymore. Okay, so that's how that works. That's what they mean by or less than the number of sign changes by an even number. Just subtract 2 till you get it. Easy? Okay, now f of negative x. So I'm going to put, so that's to the 5th, 4th, cubed, squared. Okay, I'm just writing it with the, so I can substitute. So negative x, so we got negative x, negative x, negative x, negative x, negative x. Now, what do you notice? Yeah, so let me write it. So this is going to be negative x to the 5th. This is going to be minus x to the 4th. You see that? Minus x cubed. Minus x squared. Minus x plus 5. Y'all see that? Because this is going to stay negative because it's an odd power. This becomes out of positive x to the 4th, but you have the minus. This becomes a minus x cubed. And then this comes out to a positive x squared, but you have the minus. Okay, now count the number of sign changes. Negative to negative, negative to negative, negative to negative, negative to negative, negative to positive. Only one sign change. Okay, so you're going to have 1 negative real zero. You notice there's no or. So if you were listing all of them, I would pick the -1 first because you could have 4, 2, or none positive. You could have 1 negative. So let's look at the graph. Yeah, 1 negative. So that means it had no positive. So this one had it had no positive real zeros because you don't see it on the graph. It had 1 negative. And we have a total of 5. So that means we're going to have what? 4 imaginary. 4 imaginary. So you see how I'm doing that? Without even doing really a lot of algebra, you can know what, okay, these are the zeros I'm expecting. so that you can get to the answer quicker, or get to the answer more effectively, rather. All right, the linear factorization theorem. Leave your questions on the Descartes Rule of Signs, but I like it. It's pretty cool. Okay, we're going to do this linear factorization theorem, and then we're going to do an example from start to finish, and then we'll be done, okay? Hang in there. So the linear factorization theorem, this is something that you're already doing. So again, don't try to memorize the theorem. Memorize what the steps are. It states that if you have an nth degree polynomial, it can be expressed as a product of non-zero constants and n linear factors, where each linear factor has a leading coefficient of 1. So, and I put here at the bottom, I said, so basically you're just doing factoring. You're taking the factored form of the polynomial, and you're bringing it all together to form what the polynomial looks like. That's basically what the linear factorization theorem says. You can take all them factors, multiply them jokers together, and come up with what the polynomial is supposed to look like. So these C's, those are your zeros. And then you always have some leading term. Even if the leading term is 1, you're always going to have a leading term. So here they're saying n has to be greater than or equal to 1. Why? Because if n, the degree of the polynomial, has to be greater than or equal to 1. Otherwise, you don't have a polynomial. Your a sub n, your coefficient, can't be 0, because that 0 times anything is 0. And then the C's are your zeros. I'm saying a lot of zeros. Zeros meaning your factors. Okay, so these are factors. Okay, and they're multiplied together to come up with the polynomial. Let me show you an example. So on this one, it says find a third degree polynomial. That means you're going to have a polynomial like x cubed with something, something, something. It has these 3 zeros, and it tells us that f of 0 is equal to 20. So the format, if I go back, this is the format they want us to use here. You see that? F of x, a sub n times x minus the 0, x minus the 0, x minus the 0. So let's do that. So I'm going to take f of x, and we have we don't know what it is, and we're going to take all of the zeros. What's the first 0? X minus, let me write it like this, x minus, and we have 3 of them, right? So I'm going to do x minus. You see that? X minus, x minus, x minus. And then we have a negative 5. I'm plugging in the C as they look, and we have 1. You see that? So then if I clean this up a bit, that's going to be x plus 5 times x plus 4 times x minus 1. Okay, so this is what the polynomial, this is giving us our structure. So now you're like, man, how do I figure out what a sub n is? Well, they tell us that f of 0 is equal to negative 20. But before we even do that, let's see if we can get this smaller. We can multiply all these together, right? Yeah. So multiply these two first, and then multiply x minus 1 to all of that. Okay, so let me keep going. I'm going to multiply these two first. I'm going to do FOIL, okay? First, outer, inner, last, okay? So that's going to give me, what is that? X squared plus 9x plus 5 times 4 is 20 times x minus 1, right? Because we have x times x is x squared. That's 4x. 4x plus 5x is 9x. And then 5 times 4 is 20. Now we're going to take x times everybody, and we're going to take minus 1 times everybody. Okay, so now we're going to multiply these two together. Do I have room? I think I do. Ah, cool beans, we got room. Okay, so x times everybody, that's going to be x cubed plus 9x squared plus 20x. Okay, I took x times everybody. Now I'm going to take minus 1 times everybody. So I'm going to have minus x squared minus 9x minus 20. So far, so good? Okay, let's keep going. Let's combine like terms. X squared and an x squared here, and then the 20x and a 9x. So f of x, a sub n, we have x cubed, 9x squared minus an x squared, that's going to be plus 8x squared. and then a 20x and a negative 9x, that's going to be plus 11x, and then minus 20. Cool beans? Okay. So now we're like, how do we find this a sub n? Well, they tell us here that if we set x equal to 0, then f of 0 is going to be equal to negative 20. So if we plug f of 0 in here, we're going to have a sub n times this whole thing here. And they're saying we could set that equal to negative 20. So that's what we're going to do. Okay. And then when we substitute 0 into all these x's, we'll be able to solve for a sub n. So let me show you how that's going to look. So f of, I'm going to write it like this. I'm going to put this in a bracket. Okay. Okay. And we're going to put 0, 0, 0, 0. And they're telling us this should equal negative 20. Okay, so then let's do the math. That's going to be 0, right? That's going to be 0, and that's going to be 0. So we really have 0 plus 0 plus 0 minus 20. Well, that's going to be minus 20. So we have a sub n times negative 20. I'll just do it like that. Equals negative 20, right? Because that came from here. And then looks like we got to divide both sides by negative 20 since it's multiplied to the a sub n. And when we do that, excuse me, these divide evenly. And so we have a sub n is equal to 1. So then our a sub n, or our f of x, sorry, a sub n is 1. So that's 1. You need see that's 1 times everything, or really here. That's 1 times everything. So our final polynomial looks like this. X cubed plus 8x squared plus 11x minus 20. That's our final polynomial. Check ourselves. Yep. And when we remember they told us the 3 zeros was negative 5, negative 4, and 1. Here's negative 5, negative 4, and there's 1. So see, that's how they all tied together. They all tied together. That's 1 0. That's negative 4 0. And that's negative 5 0. Okay. Which is what we saw. So let's do another one. All right. This one, they're telling us the degree is 4. And these are the zeros, 2, negative 2, 2, and I. And then f of 3 equals negative 150. One thing I want to point out, there's supposed to be 4 zeros because the degree is 4. How many do you see here? Negative 2, 2, and I. But what does that mean? Remember, imaginaries come in pair. So our zeros are really, if I were to write them right here, our zeros are negative 2, 2, I, and what? Negative I. I'll do it in a different color because imaginary zeros come in pairs. So there's our 4. Okay. So then we have our f of x, whatever it is. We have a leading coefficient. We don't know what it is yet, but we can write our 4 factors, right? As x minus, x minus, x minus, x minus. Now you're like, Dr. B, why do you have 4? Because our degree is 4. Okay, cool beans. So I'm gonna write my zeros in as they appear. So far so good. Let's clean this up. So that's x plus 2, x minus 2, x minus I, and x plus I. Okay. Okay, let's keep going. I'm going to multiply these two first, and then I'm going to multiply these two, and then we'll put them together. Okay. This already right here is going to be it's going to look like a difference of squares, and I know that's going to look like a difference of squares. So this is going to be x squared. You have minus 4. It's x squared plus 1 because, let me show you, x squared, then you have a minus ix and a minus ix and a positive I. It's x squared plus 1 because x times I, that's ix, and then a negative I times x, that's a negative ix. When you add those together, they become 1. But then when you take negative I times I, you get negative I squared. But negative I squared, or I squared, is negative 1. See that? And you have negative times negative, that's a positive 1. So that's why you get plus 1. Now we're going to multiply these together. So I'm just going to FOIL it. You get x to the 4th plus outer, what is that? X squared plus minus 4x squared plus minus 4. So you get a sub n times x to the 4th minus 3x squared minus 4. So far, so good. So far, so good. Okay, let's keep going. So this is our f of x. Now they told us that f of 3 is equal to negative 150. That means when x is equal to 3, f of 3, when x is equal to 3, f of 3 is equal to negative 150. That's what that means, okay? So then let's plug in probably don't. Okay, and that's going to equal negative 150. So 3, 3, 3. Okay, so then a sub n, 3 to the 4th. 3 to the 4th should be 80, not 3 to the 81. 3 to the 4th, yeah, 81. Gotta check the math. This was a long lesson. So 81, and then 3 times 3 is 9. Times 3, that's going to be 27, right? And then minus 4, and that equals negative 150. So 81 minus 27 minus 4, that gives me 50. Okay, so a sub n times 50 is equal to negative 150. You see that? We're going to divide both sides by 50. Those divide evenly. And then negative 150 divided by 50 should be 3. Negative 3, negative 3, negative 3. Watch the sign. Watch the sign. So my a sub n is equal to negative 3. So then my polynomial will look like f of x is equal to negative 3 times x to the 4th minus 3x squared minus 4. You'll see that? Where did that come from? That came from here, what we started with. So now we found a sub n. So my final 3x to the 4th plus 9x squared plus 12. Easy? Yep, 3x to the 4th. And you see where the zeros are? Right here. I'm assuming this is negative. I'm assuming this is 1, 0. And then this is negative 1, 0. Did they give us fraction? Let's go back. Oh, it's negative 2. Duh. You'll see that my check marks are really small. So this is 2, 0. And then this is negative 2, 0. I got that from here because they told us what the zeros were. My check marks are 2, 4, 6, 8, 10. Okay, my check marks are by 2. Okay, easy, 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 easy. All right, so let's put it all together. One last run Let's put it all together and then we are done, I promise you. So we're going to go through these steps. We're going to use the Fundamental Theorem of Algebra to say how many zeros we think we have. Remember, the Fundamental Theorem of Algebra just tells you that when you look at the, when you look at the degree, it would tell you. Use Descartes Rule of Signs to estimate possible real zeros. Remember, you look at the sign changes, and then the sign changes tell you how many positive real or negative real zeros. I'm sorry, the Fundamental Theorem of Algebra tells you, you look at the degree. The degree tells you how many zeros. And then it tells you that it has at least 1 0, which we kind of know that, but we'll go with it. Then we're going to use the Rational Root Theorem to list the possibilities. That's where you take the factors of the constant and divide it by the factors of the leading coefficient. We're going to test, and then once if we get a 0, we'll factor and we'll find the rest of the zeros. Okay, you ready? Yep. Let's do it. This is our last one, okay? So here we go. X cubed plus 2x squared minus 5x minus 6. The Fundamental Theorem of Algebra tells us that we're going to have at least one complex zero because this is greater than what do you call it? That's greater than n. So we should have, we're going to have 3 zeros. Okay? And we know it's going to be at least one complex zero. We just don't know the types, right? At least one complex zero. Now you're like, okay, Dr. Anderson, why are we doing this? Well, just, let's just go with it, okay? Okay, so we know we're going to have 3 zeros, and we know we're going to have at least one complex zero, complex numbers, real, imaginary, okay? Let's see what types we have. Let's look at the signs. Remember, we have to count the number of signs in f of x, and then count the number of signs in f of negative x, okay? Count the number of signs in f of x, and then count the number of signs in f of negative x. So f of x, I'm just going to write it, x cubed plus 2x squared minus 5x minus 6. How many sign changes? We go from positive to positive, positive to negative, that's 1, negative to negative. So we're going to have 1 positive real zero. Y'all see that? And then f of negative x. So f of negative x, let's see what we get with that. So that's going to be a minus x cubed. That's going to be a 2x squared. And then a plus 5x minus 6. Count the number of sign changes. Negative to positive, that's 1. Positive to positive, positive to negative, that's 2. So we're going to have, if I was to write this, 2 or none negative real zeros. Okay? One positive. We know we have one positive. The other two, because we have 3, the other 2 are either going to be both negative real zeros or they're going to be what? Imaginary, because imaginary comes in pairs. So we know we have at least one positive real zero. What does that mean? When we go to this next screen, pick the positive so we can get that out the way, and then it'll help us get the rest, okay? So the rational root theorem to list all the possibilities. That's where you list the factors of the constant over the factors of the leading coefficients. So we know this is plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And then this is plus or minus 1. When we divide those, we take everything up here and divide it by everything on the bottom. So that gives us plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Those are the list of all of our possibilities. 2, 4, 6, 8. So there's 8 possibilities. Okay, we don't have to test all 8, but we know that there's one positive. We know there's one positive, so let's see if we can find that. So let's test C equals 1. Let's test C equals 2. And let's test C equals 3. One of these got to work. And if one of these work, then all we have to do is factor the rest. What did I pick? C equals 1. Okay, let's test C equals 1. We're going to do synthetic division. We're already going in descending power. So 1, 2, -5, -6. My C goes here. The first number comes down. You have 1. 1 times 1 is 1, right? 1 times 1 is 1. 2 plus 1 is 2. 2 times 1 is 2. -5 plus 2, is -3. -3 times 1 is 3. This one. -3. And our remainder is a -9. That's not what we want, right? We want 0. So this is not a 0. Not a 0. So that means x minus 1 is not a factor. So next. Two plus 1 is 3, not 2. Y'all know that I know that, and I clearly jacked this up. So I want to put this in here so that y'all aren't like, she can't even add 2 plus 3, or 2 plus 1. So 2 plus 1, that's going to give me 3. So this should have been a 3. And then 3 times 1 is going to give me a 3. -3 plus, -5 plus 3 is going to be -2. And then -2 times 1 is going to give me a -2. And then -6 plus -2 is going to give me a -8. So 2 plus 1, that should have been 3. And then 3 times 1 gives me 3. So that was right. So the remainder's not 0. So C equals 1 is not a 0. That is still correct. And x minus 1 is not a factor. I just wanted to correct that last segment that you saw because it's clearly not right. Thanks. My little thing. 1, 2, -5, -6. My C goes here. The first number comes down. Okay. We have 1 times 2. That's going to be 2. 2 plus 2 is 4. 4 times 2 is 8. 8 plus -5 is going to be what? -3. Oh, +3. +3. 3 times 2 is 6. All right, that's what we wanted. And that's 0. So because the remainder is 0, C equals 2 is a 0. Therefore, x minus 2 is a factor. And we said we had one positive and we found it. It's this one. So now that we know x minus 2 is a factor, we should be able to find the rest of them. So I'm going to put right here, we know that x minus 2 is a factor. So f of x x cubed plus 2x squared minus 5x minus 6. We can write that as our x minus 2 times what? Remember, whatever's left over here, we started with cubed, so it goes down to squared. So this is x squared plus 4x plus 3. Y'all see that? X squared plus 4x plus 3. Can we keep factoring? Yes. So this is x minus 2. Let's see, does this factor x plus 1 times x plus 3? So you get x squared, 1x, 3x, 4x, and 1 times 3 is 3. Cool beans. Cool beans. And we said, what did we say? We said we had one positive zero and we had two or none negative real zeros. So if you look here, we have x minus 2 is equal to 0, x plus 1 is equal to 0, x plus 3 is equal to 0. Let's solve all of them. Add 2 on both sides. This one we're going to subtract 1 on both sides. And this one we're going to subtract 3 on both sides. So here we have x equals 2, which we knew that, right? Here we have x equals negative 1. There's our first negative. And here we have x equals negative 3. That's our second negative. So those are the zeros. So you see how they all come together? We're not memorizing the theorems, we're memorizing the tools that can help us get through all of the logic. So cool beans, cool beans, cool beans. And here's the graph. Yep. So this is 2, 0, right? And then negative 1, 0. I hope I negative 3, 0. Y'all are like, Dr. B, you got to know what numbers you got. Yeah. Okay. So those are the 3 zeros. Okay. Cool beans. Cool beans. All right. So common mistakes. Trying to memorize these theorems and getting them mixed up. Don't do that. Don't do that to yourself. Unless you have to memorize the vocabulary, don't do that to yourself. Focus on the logical steps. I need to know, do I have any zeros? Yep. I have at least one complex zero if the degree of my polynomial is greater than or equal to 1. Cool. What's the list of real zeros? Or, matter of fact, start with Descartes' Rule of Signs. How many positive real zeros do I have? How many negative real zeros do I have? Boom. What's the possible list? Here's your list. Choose from the list. Boom. And then you just start working your way through till you find all of the zeros. Don't confuse real with complex. Complex numbers is the cloud. Everybody's in the complex numbers, and then it goes from real, imaginary, real, imaginary, real, imaginary. Complex breaks down into real and imaginary, okay? Don't forget, just because you have all these possible real zeros, it doesn't mean that those are the zeros. You have to test them. Use synthetic division to test. Is going to be the fastest. If you can factor, but a lot of times it's not easy to factor. There are other ways you can do it, but this is just another method. And don't forget, you can have imaginaries. Imaginary zeros come in pairs. The rational zero theorem, list all of them. Sometimes you can have 30, no, let me not say that. You can have a lot of them. List all of them, but if you've done the work up front, you can kind of figure out which ones you don't even need to do the synthetic division on, because I don't want you doing synthetic division 50 times. You're going to be mad at me. If a zero occurs multiple times, okay, yeah. So sometimes you can have a zero that is the same zero. It can occur multiple times. That's okay. You still count it. So just like this one, like if 2 and negative 3 are zeros, you still have 3 zeros, even though 2 shows up twice. Always, 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 always check behind yourself. Y'all know I always say that. Check behind yourself, because the signs get real. You saw I started getting tired. I was making up numbers. That happens, okay? Key takeaways: the zeros tells us where the polynomial equals 0, but not all zeros appear on the graph. The only ones that appear on the graph are going to be your reals. Your imaginaries aren't going to appear on this particular graph. There is a special graph for graphing imaginary numbers, but that's another class, so don't even worry about it. In this particular topic, you won't see all of your zeros on the graph, but you'll see the real zeros on the graph, okay? Do not memorize. Try not to memorize these theorems. Memorize the steps. What do I need to do? How many zeros do I have? Do I have any zeros? Here's my list. Test in the list, factor, okay? Follow the steps every single time, and I think you're going to do great on this. Remember, at any time, send me your questions. So you should be able to complete all of your assignments with success. Remember, some of the questions may be easier or harder than others. That happens because you gotta get your thinking going. Follow the steps that we covered in this lesson. Write down the steps so you can see it. It's quick to just do it in your head, but if you miss a sign, sometimes it's hard to go back. Write it down in your hand. Ain't no shame. Keep your calculator handy. Ain't no shame in it. No shame at all. And remember, at any point during the videos, you can leave comments. You can leave questions. I am always happy here to help. All right? Cool beans. Talk to y'all later.